subset of again X, correct? Because the domain, that's what is better to write T from X to X, so that for each X in X, Tx is a non-empty closed convex subset of X. So what we take in Kakutani fixed point theorem, the domain will not take the whole space. Suppose we take the domain the whole space, what will happen? Domain we don't, then under suitable condition it can have a fixed point. It is a Banach space. Then we require a very, like even we have seen that R to R also. Even we have seen that closed, even R to R, X goes to X plus 1. Translation map. It is a nice isometry map. It does not have fixed point. So we cannot expect that type. So what we have is compact convex subset of a finite dimensional nonlinear space. K, non-empty always, compact convex subset of X, finite dimensional nonlinear space. T from K to K, say that these are already compact convex. For each X, Tx is compact also we can say, because closed subset of the compact set is compact. Okay, we will tell even compact convex. So further for each closed subset of K, C closed subset of K. It is a subset of K, also closed. Will it be closed in the original space? C is closed because K itself closed. Okay, C closed subset of K imply, suppose T is a map from K to K, single valued, or we call it F in this. Y belongs to K. What is F inverse of Y? Those X in K whose image is Y. Say that Fx equal to Y. But here Fx is a set. Here it is a set. Then what we should have? Here F inverse of again, if C is a subset of set also we define inverse image of F inverse of C. How we define? Set of all X in the domain. Okay, domain, suppose domain came in, domain is K, so that only one element means that Fx equal to Y means what? That belongs to, Fx belongs to singleton Y. So here it is what? Fx belongs to C, all the three images. But here it is a set. So that is, it is Tx, that case what we say that, not in this case, we can, that is very strong. So we define this as all X in K, so that Tx intersection C is non-empty. Suppose if it is single valued, Tx single valued means Fx belongs to C. So this is called pre-image of a set under multivalued map. So C is a closed subset of K, then the inverse image T inverse of C is again a closed subset of K. And suppose whenever C is a closed set, inverse image of closed, if it is a single valued continuous map means what? Inverse image of open set is open, similarly equal inverse image of closed set is closed. Here if whenever C is a closed subset of K, inverse image is again a closed set. Then that map, multivalid map, is called upper semi-continuous. It is not same as f from x2 or lower semi-continuous upper, it is multivalid map. It is called upper semi-continuous. Similarly, whenever C is an open set, then inverse image is open, then that is called lower semi-continuous. See, this concept we can define more generally: X topological space, Y topological space, X goes to Tx, subset of Y, then inverse image of closed set is closed mean upper semi-continuous, inverse image of open set is open mean lower semi-continuous. If it is both lower and upper mean continuous. There are even we can say the what is called metric projection. Best set of all, if A is a, it depends upon the time I will give that example. Okay, now what is Kakutani theorem says is the domain K is a, what is the domain? Compact convex subset of a finite dimensional nonlinear space. T from K to K, a set valued map or multivalued map, satisfying what condition? And again we are assuming that for each x, Tx is a compact convex set. We will assume non-empty compact convex set. Further, T is upper semi-continuous. Upper semi-continuous. Then it has a fixed point. Then there exists fixed point means then there exists x in K. Under that condition there exists x in K and x belongs to Tx. In our case that x is some order pair x naught y naught belongs to T of x naught y naught, that is equal to T2 of x naught cross T1 of y naught, like that. So now we are having here, for example, this clear? So that means under suitable condition we can use Kakutani, almost we have done the proof of that. In fact, it is f is a assume even continuous function. For convexity we can lower semi-continuous mean for minimized case, upper semi-continuous maximized case, we can assume that concave, like that. We want that our set should be T1 of x naught, T2 of y naught convex set. So we will assume suitable condition. So that for each order pair xy, T of xy is a nice compact convex set and domain m cross n is compact. Under that condition this T is upper semi-continuous. Hence it has a fixed point by Kakutani's theorem. Now that implies, now x naught belongs to T2 of y naught implies x naught, what is this implies? X naught belongs to T2 of y naught implies what? What is that? X2 belongs to T2 of y naught means what? What is? It will both. X naught belongs to T2 and y naught belongs to T1 of x naught. So this implies f of x naught y naught. Here it is here. Once an element is here, that gives the maximum profit. For whom?
For player 1.
Player 1, and similarly here player 2. That means this will give you, this is greater than or equal to f of, when we selected x naught, if is that, this will give the maximum profit. Similarly for G, that means this order pair x naught y naught will give the maximum profit for player 1 and 2, and that existence theorem comes from fixed point theorem of multivalued map. Later this theorem has been, Kakutani's theorem has been generalized in many directions. One of the, somewhere in late 50, I think National Academy of Sciences USA. Kyphon or kyphon we call it. Again K compact convex, only we can assume Banach space or non-linear space. What is important there done is for locally convex topological vector space, and it is a multi-valued map. Again for each x, Tx is a closed convex set, the map is upper semi-continuous, then it has a fixed point. Essentially it is a generalization, but it is not our simple generalization of, using some non-trivial, highly non-trivial. Kyphon, later Himmelberg, and much later even 1992, one Lassalle from France, what he did was factorize. T is a map. What is the image? Main thing is strong condition is convex. He assumed that T1 composition T2 type. More generally for N map. So each factor, this is T1 of T2x. He has assumed T1 of T2, that means T1 of y is convex, T2 of y is convex, but the composition may not be like something we sometimes if we do like this. See, suppose we have a square in R2. See, all the element goes to, let us say, here. Every year we fix it, compact, anything. So all the element from this set goes to here. That is T2 of x or T1 of, then here the nearest point. We have a nearest point, this is called nearest point. Then what is the this will become, first it goes to here, then comes here. So like that. But individually what is, for each x, this is a straight line, which is a convex set. But if then for each element here, it goes to only one point. Again a singleton convex, but what is the image of a set? See, not T1 of, here it is T1 of T2x. This whole line. Then this will be T1 of some A, union A belongs to that set. Then that need not be a convex set. So that is a nice result he proved in 1992 in Journal of Mathematical Analysis and Application. I think there also he has given some application to, I think similar to.
Anyway, we cannot say a convex union of convexity.
That's it. Union of, that's what that's what exception.
Is true. But
union, that's what here. Here the union of convex set, that's why it need not be, convex set need not be convex.
Yes.
But what is the beauty of that result is, each T1x is convex,
Yes.
T2x is convex. The original map, x goes to Tx need not be convex valued, but still it will have a fixed point. That is further generalization of this whatever.
This is only possible when one contains another.
Which one?
This is possible, the union part. One contains another. T1x is contained.
We don't have it.
That is possible.
Then it will become only one set now.
Then they will make it one set.
Then it is nothing but one.
One set.
Okay. So just to, because upper semi-continuous, I will just start with one example, which is the motivation for our next best proximity point also. Then with that we will stop. Even we will start with the metric space. A, capital A, non-empty, compact, convex, subset of a metric space, we will write for metric space X min X with D. See, we have a metric space X. We have a set A which is compact. To each point X, we want to find the nearest. So that's someone come from Bilaspur. So we want to some communication tower. We want to fix. We cannot fix somewhere. We can fix outside. We will not like the radius and all those things inside, no. But you select in such a way that that is the nearest to the city, not nearest to that way. What we want is for a given X, find the nearest point from Y, from A, that is what condition actually it should satisfy? Distance between X, Y, among, you take any point here, A, distance between X and A, X and Y, X and this, all this thing. Among that we want to take the nearest point. That means a point Y in A is said to be a nearest point to X, is said to be a nearest point to X, nearest point to X from where? From the set A. If and only if, okay, what condition you tell? Oh, I am not, I wanted to write something, so incomplete, you tell. What is the condition? Which is nearest? See, I am standing here. Who is the nearest to me from this group? Professor Dhananjay Gopal, because distance from X and Dhananjay Gopal, X and this, among all the things. So that is the nearest. That means what? Distance between X and Y less than or equal to distance between all other points. To that set A. A only we have called, okay. For all A. If that such a point means, we call it distance between already this, everything is, then this point is, what is the relation between this X is in A, then we define normally what we define this, distance between X and Y equal to infimum of distance between X is, I mean, we cannot define infimum of distance between X, Y is itself X and A. Infimum of distance between X and A, such that A belongs to capital A, like that. Such a point X is, if it is a compact convex set, and that means if the understood, it is something called approximatively compact, which was introduced by, I think, Finolo or something. You can see that one approximation theory by Singer or some in non-linear space. I mean, very artificial, look like artificial, but again it has very interesting application later. See, we want to find a nearest point. What is this? Distance between the point X and A. We have seen that infimum or greatest lower bound of distance between X and A belongs to A. This implies that this under here infimum is the X, I mean lower bound is there, this exists. Then we call alpha. Alpha is already among the lower bound, among the lower bound the greatest. If we give any natural number n, then alpha minus 1 is not a lower bound. That means what? Not a lower bound, because that itself already greatest. This cannot be a lower bound. That means what? There is at least one xn xn or a, call it xn from a such that distance x and xn is lower bound. Lower bound is less than or equal to, now this will be greater than alpha minus 1 by n. Already this is a, then immediately prove that you can alpha, I have written correctly. Okay. Whether xn converges to x, we cannot, there exists a sequence xn in a which converges to alpha c. What about alpha less distance between x and xn? Because xn is in a, this is lower bound, but this is less than, if you want write that alpha. So that means what?
Limit is alpha.
Limiting case, it we can prove that, okay, complete xn, so properties of infimum and supremum is alpha is supremum of x, x in a means there is a sequence which converges to the infimum or supremum. So that will complete. So that means what? We will get a sequence in A such that distance between xn and x converges to distance between the point xn set. Okay. Now, but what we are searching? We are searching a point in the set A. So what will be the some artificial condition, that's why xn is a sequence in A. Suppose if that sequence itself converges, then we can the x goes to distance between the point x and A is a continuous function. A point, a non-empty set in a metric space, x image is distance between the point x and set A. Distance means infimum, distance between x and small a in capital A. That is not a metric. Then it converges means we can take the limit both. Suppose xn converges to y. That means limit distance between y and x less than or equal to xa. So then that will imply distance between xy equal to distance between xa. So motivated by this, suppose this such sequences are called, there may be more than one sequence. X is in capital X, xn is a sequence in A, so the distance between xn and x converges to distance between x and A. Then such a sequence is called minimizing sequence. Okay, forget about the name. If this is so, then xn has a subsequence which converges to an element in A. Then that is called, if such a thing happens, that set is called approximatively compact. In R, every closed set is approximately compact. In a finite dimensional vector space, every closed set is compact. In a Hilbert space, closed convex set is approximatively compact. See, but note that even unit ball in an infinite dimensional space cannot be compact. It is closed convex, but it is approximatively compact. That's why we may feel, what is that so artificial, but that is sufficient, that artificial condition sufficient to get set of all best approximation, nearest point. Then for each x, yes. So we have a map X metric space, or X A is a approximatively compact convex set. That's why don't worry about approximately compact. Compact set, just a compact subset of a metric space. Then this we call it P suffix A of X. That is what? Those elements in A such that distance between, that is the nearest point. Distance between x and y equal to distance between x and A, like that. This is non-empty. That means it is a set valued map. And this, that means x goes to Tx. In this case, it is P suffix of x, a compact set exercise. This is a upper semi-continuous map. Anyhow, thank you very much. Extra few minutes extra because we took some extra time, tea time. Okay. Thank you very much. And if you have still any question, please feel free to ask. But the exercise, some of the exercise, please try your best and feel free to discuss if you are not able to solve or if you want to discuss.
Thank you, Professor Veermani. You have discussed multi-value maps in the context of fixed point theory, Nash equilibrium point. Really, in game theory, the Nash equilibrium is very important. We know actually theoretically, without knowing the equilibrium, when you apply in the game theory, we have a good number of occasions that we use this equilibrium. But it is in the very idealistic mode only, idealistic condition only. Then only the Nash equilibrium is applied. But in the, I think in the real world scenario is very difficult.
Yeah, that is.
Real world, because there is no equality. If equality is there, means like demand and supply. If you talk about the demand and supply is fine. If the demand is there, supply is there, and they coincide, then it's fine. If they don't coincide, then the issue comes. And okay, this is a really very interesting part of functional analysis. But you will wonder to know that in artificial intelligence and the machine learning, the game theory has paved a pivotal role. And now these days, AI students are offered one full course in game theory, AI and ML students. Yeah, in triple IT, most of the triple ITs, they are offering complete one paper in game theory, machine learning, and later on followed by the deep learning. So they are training the machine for the such games. So they use the Nash equilibrium and all sorts of games what we have done. Apart from that also, how you can see in your emails, the filters are there. Apart from the filters, the machine has trained in such a manner that all the incoming mails, they are sorted out into spam as well as your inboxes. So you have seen that this is the recent development only because of the AI. And they move to the spam, and there are the occasion also sometimes. Suppose I don't know Professor Veermani, and Veermani is sending me the mail. And actually the firewall is so strong that my machine could not understand that this is the mail from Veermani who knows me very well. So unless I say that yes, Veermani is known to me, it will not accept as an inbox mail, it will send it to the spam. So there is the chances that inbox mails also may go to spam, and there are some spam mails which are supposed to move to the inbox. There are the mails that they are in inbox, they have to go to the spam also. So here the concept of the game theory comes. Here we use the probability also in game theory. So rightly he said, of course he is using the multi-value mappings, etc. If you read the Hilbert space theory and applications, you will find at the end there is an application in the game theory also. In Hilbert space, that is H1 cos S2. Yeah, you are talking about the Cartesian product also here, the same thing. Really it is very interesting. So if you, those who have a little bit interest in the programming part also, they can use it for the programming. And finite dimensional, anyway your machine is not infinite. Your data is always finite.